Well, good morning, everybody. I hope that you are all doing well. I hope that you had a nice weekend and that you're ready for the brand new week. Although I guess the brand new week started yesterday. I'm so screwed up. My Monday, on Mondays, I feel like this is a weekend, but then everybody else is like doing like going to work. I don't get it. I'm not used to this Tuesday, Thursday thing. Anyway, hope that you guys are doing well. Is everybody getting uh, a little bit the hang of these EROs? Or is everybody getting frustrated by it? I warned you, didn't I, last week that, yeah, this assignment with all these elementary row operations, it's kind of a pain. Um, I just want to reassure you guys about something really quickly, though. If you are making little goof ups with your elementary row operations, that's not the same thing as saying that you don't understand the material, right? I know some very, very good math students who understand exactly what they're supposed to be doing. They know what this is all about and they can sort of get the process totally right. But they make little typos, like they miscopy, and somebody last night in my office hours literally just miscopied the matrix right at the very beginning in their work. And so the whole thing was all thrown off. Or there's a sign error that comes in, or you accidentally have the wrong number written down somewhere, right? And so if that happens to you, say 2 or 3 or 4 times, you start to be like, well, maybe I don't understand this material. That's not necessarily the case, right? You might really well understand what's going on, which is actually the most important part. And it could just be that, yeah, you were tired or you just weren't focused, or something like that might have gotten in the way. So as frustrating as I know it can be at times, try not to get too discouraged about, you know, the perfectionistic mindset that I think a lot of us get caught into with these EROs. Even myself, right? I will screw up an ERO from time to time as well. Or even, you could say, well, if I studied harder. Well, not necessarily. Like if you study for 200 hours for this class, right? You could still make those same kinds of silly zombie mistakes. In fact, you might be more likely to make them because you didn't get enough sleep in the process. So anyway, that's just something to keep in mind. Try not to beat yourself up if you're having a few of those kind of issues. I do have a lot of office hours today. We have 2 assignments that we're going to try to have you turn in today, right? They are number 5 and number 6. I have put some space over here for some questions, and I'm going to take some of those today during class, but I also have office hours all the way until 10 o'clock tonight. So if you need to come into Zoom or in person, I'll be around. This is pretty important, these 2 assignments. So I definitely want you kind of getting on top of that. Okay. Let me make a couple of announcements here and then we'll jump in. The big thing, which I did put in my email over the weekend, is I decided to move your midterm. It's supposed to be next week on Tuesday. I decided to move it until Thursday so that I could make sure I have enough time to really do justice to chapter 3, which we're going to start today. So just be aware of that. Midterm 1, I am moving that to Thursday of next week. So that would be September 26th. Okay. Let me take just a moment and talk about this. If you go into Canvas, there is, of course, I've gone through this with you before. There's a files section over here. You click on files, and then one of these folders says midterm 1 resources. I'm just going to open this up for a second and show you that there is a bunch of stuff that I prepared for you here. Now, nobody should feel like they have to do all of this, okay? It kind of depends on how much time you have, how comfortable you are with the material, that sort of thing as to what you want to do. Let me just kind of tick off what these documents are, though, so you kind of know what is here. I actually have 2 sample midterms. So if anybody's wondering, I wonder what Dr. Annan's exams are like. I'd like to see an example of what his test could look like. I actually put 2 of them here. One of them is in all caps and one of them is in lowercase. And you'll notice that not only do I have the midterms listed there, I also have the solutions also in there. And the solutions are fully worked out, like detailed how you would solve the problem. My advice is don't just like go read the solutions though. I would actually suggest that if you could only do one thing to study for the midterm, it would be good to print out at least one of those exams blank and take it as a sample. Just give yourself 2 hours. You're gonna have the whole class period, so give yourself 2 hours, sit down and just see how you do with it. And then you can go look at the solutions after that. The problem is if you sit there with the solutions to begin with, then you're not really assessing yourself as to where your strong points and weak points might be. So I would definitely recommend that you start off by, taking one of them as a sample test. And if it doesn't really feel good to you, you can always take the other one as well. So I have 2 of them there. You can look at both of them. You'll see that they're similar. They're not obviously the same. And your exam will obviously be yet different again, but it should be similar length, similar number of questions, right? The types of questions I ask and the breakdown between the different chapters. You kind of get an idea if you look at that. So that's what these 4 files are the 2 sample tests and their solutions. I also have a review packet here. So in fact, let me open up that review packet. In this midterm 1 review, see if this will open up for me. This has, so you see I already updated the date to the 26th, next week on Thursday. I have extra office hours listed here. I have what the exam is going to cover. So chapter 1, chapter 2, and this week we're going to do chapter 3, which is 3.1 through 3.3. So these sections of the book. And then I've listed out kind of some of the buzzwords, like the important, like highlight words that everybody's going to want to know before we take our exam. So that is chapter 1, chapter 2, chapter 3. And then I have a whole big long bullet point list of what are all of the things that you should be able to do for this exam. So you should be able to solve a separable differential equation. You should be able to decide if a matrix is symmetric or skew symmetric. Find the rank of a matrix, solve Bernoulli equations, right? So you can go through this checklist. I would actually think of it like a checklist. Look through that list. If you come to a bullet point that you're like, oh, gee, I forgot about that, or I don't quite remember how to do that, then you can flag that for yourself to go back and look at it later on. So anyway, it's a big bullet point list. In fact, it goes on to the next page. It's kind of long. It goes on to the next page, several more things. The part here on this page is mostly about the chapter 3 stuff. So we'll be talking about this next couple of classes. And then I have some advice about kind of some things to study. One thing that I did is I recommended that in chapter 1, remember that was the chapter about separable, linear, Bernoulli, and homogeneous differential equations. You haven't had a lot of practice with seeing those equations kind of mixed together. Right, when you were in section 1.4, everything was separable. In section 1.6, everything was linear. In section 1.8, everything was Bernoulli or homogeneous. So there's actually a review section in the book at the end of chapter 1 that has practice on all of those equations mixed together. And it's actually a whole bunch of problems from 16 to 42 in that review. And I actually printed out solutions to all of those. This thing up here at the top that says chapter 1 review problems. Well, that's the solutions to those 16 through 42 from the review at the end of chapter 1. Again, guys, I don't expect you to do all those problems, right? This is just, I would rather do my job and give you like plenty of things to look at if you need them. But I imagine most students aren't going to spend the time to do 25 extra problems out of the chapter review at the end of chapter 1, right? I just wanted it to be there for you in case you're interested in looking at that. Anyway, so there's a review packet. I didn't scroll all the way to the bottom of that packet, but if you do that, you'll see that there's even some more practice problems there. And so I have solutions to all of those practice problems. Everything that is a sample problem, I always have the solutions to those, so you can review how to do them. So that's what these 2 files are about. And then there's review session. So I have a little document with some problems that I actually made a video for. So I'm gonna come over here to the pages section of Canvas, and you'll notice in the pages section, this is where I keep all the videos. There is one here that says midterm 1 review session. So if you don't like just reading solutions, you'd rather listen to my voice over the weekend or something, right? What you could do is go in and just watch these review sessions. And the problems that I'm doing in that review session are in that handout, that document that I was just sharing with you. So each of these is like a 30-minute clip. It's not really organized all that precisely. Like I think I jump around a little bit between the topics here. It's not just done directly in order or anything. But if you're willing to, I don't know, spend whatever it is, about 90 minutes kind of watching those videos, you can sort of see me going over a bunch of sample problems that hopefully covers the material pretty well. Again, totally optional. You can take it or leave it. I just want it to be there for you if you think it might be helpful. Okay. Again, every student is going to have maybe a slightly different way of approaching the exam. For some students, maybe you don't want to get too wrapped up with this folder and you'd rather come to office hours, which I have a lot of office hours and kind of directly working with me on getting ready for the test. That's also fine. But I do want this to be available for those of you who maybe would rather study from home and kind of do things on your own schedule and everything. You can certainly do that as well. So what my general sense is from my past years of teaching the class is that this is probably too much stuff. Like you would be really a gold star person if you actually did every single thing in here and be like, wow, that's amazing. So just take bits and pieces of whatever you need. As you start studying, you're going to figure out what your strong points are, what your weak points are, and you can start focusing on those things as you're looking through these materials. So there will be, what I will say is nothing is left out in terms of what we covered. So if there's something that you're wondering about how to do it or you need a review of it, you're going to find it somewhere in here. There'll be a practice problem, there'll be a video solution, there'll be something that's in there that should help you with that. Okay, so anyway, I wanted this to be up for you. We still have 9 days to get ready for this test. Whenever you have some free time, particularly this coming weekend would be a good time to maybe start diving into this and taking a look at some of that stuff. Okay, so any questions about that? Thomas?
If there's like an integral that turns into like inverse tan or something, are we given a table for that?
Yeah, you'll have a table of integrals. So if we go back to the files section of Canvas again, there is a folder that's called special handouts here. And if you click into there, up near the top, there is a document that says annihilators and integrals table. And this is what I will be giving you on the exam. Now it says annihilators and there's this stuff at the top about annihilators. We're going to cover that in November. That's for much later in the semester. For right now, it's really just this table of integrals down at the bottom that you need to look at. So I'll definitely be giving that to you. Other questions? Okay, well, anyway, so this is all here. I encourage you to dive in at your leisure whenever you have a chance. And if you have any questions about any of that stuff, do let me know. I will not be reviewing for the exam in class per se, Tuesday, Thursday at 10 o'clock. We're going to keep moving on. We have lots of stuff to do. So it will be a little bit on you guys to take the initiative to actually look into those resources on your own. But anyway, that should hopefully be a little bit of guidance for you. Okay, so I went over that. Great. So before we jump in any further, I said we're going to start chapter 3 today. But before I do that, I want to warm up with this problem that's over here on the sideboard. I realized I kind of forgot to do this on Thursday last week. This is actually a couple of items that are in the book. I can give you the references here. This is theorem 2.6.10. So that's in the book, and I didn't cover it last week. Also, I should also mention that the first item is actually also in the homework that you're turning in for tonight. It's actually true, false item F. They ask you, is it true or false? If matrix A and matrix B are both invertible, is A times B invertible? And the answer is yes, that is true. And this statement justifies it. Okay, so what I would like to do actually is show you how to verify. This is going to be a proof. Okay, start off with a little theoretical problem here. If I start with two matrices that are both invertible, then when I multiply them together, the new matrix is still invertible. Okay, remember guys, with true false items, I don't just want to see whether it's true or false on your paper. I want a brief little quick reason. And it can be very short. You don't have to be super long-winded about it, but I do want to see something more than just the answer, true or false. So for example, for number one, which I'm going to solve right now, we can write down a little solution, which I'll do in blue here for you. So I'm actually doing part of your homework for you, as well as kind of looking at this theorem, this result in the book. So what the claim is that the product of two invertible matrices is still invertible, and that the inverse of the product is the product of the inverses in the opposite order. Do we remember seeing something like that earlier in the semester with something else? Anybody remember that? Where we had A times B with a certain operation gets swapped around. Blake?
It's the associative property.
The associative property is actually the one that just says that you can switch parentheses around. You're in the right train of thought as far as what I'm looking for, but I wasn't looking specifically for that. I'm wondering if anybody can remember a property that's kind of like this one, but not with inverses.
Wasn't it with transpose?
With transposes, right? Yes, exactly. So you may remember when we made a list of properties about matrix algebra, we saw that with transposes, we have the same phenomenon, which is that when you have the transpose of a quantity of A times B, it flips the order of the matrices around when you multiply the individual transposes. So this is the same exact thing, but for inverses. Okay, so let's actually try to justify that the inverse of A times B is B inverse A inverse. And I'm wondering if we know what's required in order to do that. Because actually, this is the same thing you have to do on 35, 37, some of these problems at the end of section 2.6, they're kind of the same idea. If I want to prove that the inverse of one matrix is another matrix, how would I do that? If I have matrices X and Y, and I want to show that they're inverses of each other, mathematically, what would that mean? Like, how would I convince myself? Blake.
Multiplying together will give you Ivan.
Exactly. Yes, yes, yes. This is something I definitely want everybody to be comfortable with. When two matrices are inverses of each other, when I multiply them together, I should get I, right? So let's try it here. Let's try it on this number one right here. The inverse of A times B is supposed to be B inverse A inverse. Let's try it. Let's take A times B and let's multiply it by the B inverse A inverse. So I'm going to basically take these two matrices and multiply them together. Notice I don't have a -1 exponent on the AB part. That's because I'm proving that the inverse of AB is this thing over here, whatever it is. Okay, my goal with this is to simplify it down to I, the identity matrix, right? That's what I want to do. Can you guys remind me, do these parentheses matter? It's kind of what we were looking at a moment ago here. The associative property just says, yeah, it doesn't matter how you do your parentheses, it's the same result. So here's what I'm going to do, guys. I am going to put the B inverse, which is in the center, inside some parentheses. And what is B times B inverse equal to? I, right? The identity matrix. So this is A times the identity matrix times A inverse. Remember that the identity matrix is kind of like multiplying by 1. So do we need to write it down really? We can drop it, right? It's kind of like a silent matrix there that doesn't affect anything. So I'll just get rid of the identity matrix. And now I have A times A inverse. And what does that equal? the identity, exactly. And that we'll put a check mark next to. That's what we wanted to get. That's what we wanted to get. Okay. So that establishes that the inverse of A times B is equal to B inverse A inverse. It's exactly what we wanted. Does that make sense to everyone? Let's try the second one. Notice it's just a one-liner. So if you put this in your homework on true false item F, good to go. It's exactly what you want. It is a true statement, and that part in blue explains it. Let's look at the second one. Something similar for the transpose. If I take the inverse of A transpose, it's the same thing as if I take the transpose of A inverse, right? I can switch the order of those two things. Okay, and this is going to help us with, this actually helps us with another one of the homework problems for tonight. So what I'm going to do, I'm going to take the matrix on the left, which was A transpose, but without putting the inverse on it, I'm going to multiply it by what its inverse is supposed to be. Okay, so I'm claiming that the inverse of A transpose is this matrix. So again, I'm going to multiply them together and make sure that I get I. That's the idea. Okay. Ooh, what can I do with this? I have something transpose times something transpose.
Using the transpose.
This was quite good timing, right? With the transpose, if I take two things transposed together, I can put it as a single transpose as long as I switch the order of the two things. So I'm going to do exactly that. Guys, this is, you can think of this as the B transpose A transpose in that notation over there. So I'm going to switch the order. So I put the A transpose on the left, the A on the right, and I do the whole quantity transpose. This is exactly that property that's over there on my other board. Okay, does that make sense? And now what do I have inside the parentheses here? That's just I, right? The identity matrix. So IN transpose. What do you get when you take, let's just remember what our identity matrix is. Remember the identity matrix looks like this essentially, right? What am I going to get if I transpose that? Same thing, right? It doesn't, when you flip the rows and columns, you sort of reflect it across that main diagonal. And when you do that, the matrix doesn't change, right? The identity matrix stays exactly the same. So I could just drop the transpose and I immediately get the identity matrix. So we can check that one off as well. That's exactly how you do it. That's exactly how you do it. Okay. Are we all good with that? So that's a nice warm up. And I will tell you that when you're looking through the midterm resources folder, you're going to see some examples like this. By the way, the more times you see these examples, right, they're mostly written by me. So you know it must be something I think is worth studying. And it's important to understand. Let's do a couple of problems from the homework now that we've kind of warmed up here with this. I'm going to switch back to the homework for a moment. And I'd like to look at 2.6 number, well, I'm actually, nobody put 34 on the board over there, but somebody wanted it, right? 34? Yeah, that's what I thought. Okay, just checking. So yeah, let's do 34 as well, because I think usually people have a question about this one. This just says, if A, which is n by n, is invertible and symmetric, right? Then A inverse is symmetric. So if a matrix has an inverse, and if it was symmetric to begin with, then the inverse is also symmetric. Can somebody remind me what the equation is for symmetric?
It's when like across the diagonal,
Mhm.
the ones on the triangle are flipped.
Exactly. So whatever's in the northeast corner of the matrix has to be a mirror image of whatever's in the southwest corner of the matrix. Does anybody know an equation that That's it. Thank you so much, Marco. The A transpose equals A. So this just, let's write that down. A being symmetric just means that when you transpose the matrix, it stays the same. Okay? And now what am I hoping to show here? Are you ready for the solution to this? Guys, please don't blink or you're going to miss it. It's literally, it's almost immediately true. I want to show that A inverse is symmetric, meaning if I transpose it, it should stay the same. Let's check it. If I take A inverse and I transpose it, does it stay the same? Well, the minute I see this on my paper, I'm immediately drawn to what we just talked about here on item number 2, right? The inverse of the transpose of A inverse is the same as A transpose inverse. So this is by theorem 2.6.10. I guess I'll just say theorem 2.6.10. The thing we just warmed up with over here. Oh, but now I've got A transpose in parentheses, and since A was symmetric to begin with, I can change the A transpose to the A, and look at that. That's the whole solution, because the transpose of A inverse is the same as A inverse. That means A inverse is symmetric. We're done with this problem. It's almost so short that people get nervous. It's like, wait, this can't be that short. There's got to be something wrong with it. After doing pages of EROs, it's like, how could anything be this short? But it actually is that short. Okay, is that okay to everybody though? It's short, but it's also, I'm not saying it's easy. Like if you haven't done a lot of theoretical items in the past experience that you have, something like this could like have you scratching your head for a few minutes, right? That's okay. That's okay. You haven't done a lot of these kind of problems. I totally get that.
Could you just explain it one more time?
One more time, sure. So to prove that this is what I'm focused on, right? This is what I want to explain. Why is it that the inverse of A is still symmetric? So what I have to prove is that the inverse of A, when I transpose it, stuff in the middle, it should get me back to the inverse of A again. Like I know that this is the structure of what it means for a matrix to be symmetric. When I transpose it, it's just the same as what I started. If you're not remembering symmetric very well, don't forget it's on that handout that's also in that special handouts folder. There's a square matrices handout in there. And also I asked you to watch a 7-minute video about it a week or so ago. So you'll be able to review it there if you need to, but that's basically it. So you have to do something in the middle here to explain why is it that the transpose of this matrix is the same as this matrix. And the stuff in the middle turns out to be one thing, which is just, oh, we just showed over there that I can switch the inverse and the transpose around. And then the thing that's now inside, right, the A transpose is already equal to A. So I just take the A transpose, put A in its place, and now I have the inverse of A there on the far side. So that's it. That's the whole ball of wax. Okay, so that's 34, which I understand that wasn't one of the ones on the board, but that's okay. Let's do 35, which is on the board over there. So I'm going to do number 35. This is for the homework that's due tonight, right? This is actually for the second assignment of the homework that's due tonight. So 35 is asking us the following. It says, let A be n by n with A to the 12th power equal to 0. And where it says equals 0, we of course have to interpret that as the 0 matrix, because it is a matrix. So I'll write it as 0 sub n. And then it says prove that if we take the identity matrix minus A cubed, that it has an inverse, and the formula for that inverse is going to be equal to the identity matrix plus A cubed plus A to the 6th plus A to the 9th. So this is number 35. Again, very theoretical. This is a very theoretical problem. Okay. So anybody got a strategy for me on proving this? Nathan? Exactly, if two things are inverses of each other, when we multiply them together, we should be able to get I. Right, anytime two matrices are inverses of each other, even if it's written abstractly like this, right? If there's two matrices that are inverses of each other, when I multiply them together, I should get I. Let's check it. Let's check it. So this is also, guys, a very short solution. So I take the matrix on the left, which is the identity minus A cubed, and I multiply it by what we are proposing its inverse to be, which is the identity plus A cubed plus A to the sixth plus A to the ninth. I want to sort of multiply this out, and my hope is that after the dust settles on this calculation, that I'm actually going to get I. It's the same thing we just did twice over here already. We're just doing it a third time now. Okay, so let's try it. Now, here what we have is a multiplication distributed across addition and subtraction, and that, if we go back to our matrix algebra, that was a legal property. The distributivity law does work for matrices. So I can FOIL this out. That's what I'm trying to say. So I can take identity times identity, right? That would be, so let's actually just distribute the identity to all of these terms first. So that'll give me the identity squared plus the identity times A cubed plus the identity times A to the sixth plus the identity times A to the ninth. And then I have the minus. I'm gonna have to use a second line here. On the minus, I have A cubed times all of these things. So now I'm gonna distribute the A cubed to all of these four terms. All right, so I'm just distributing it. So that would be minus A cubed times the identity, minus A cubed times A cubed, which is actually A to the sixth, and then minus A cubed times A to the sixth, which is A to the ninth, and then minus A cubed times A to the ninth, which is just A to the 12th. So all of that is just distributing it out, foiling it out into a whole bunch of terms. Somehow, this is supposed to just become I. Right, at least we hope so. That's what we're trying to show, is this is just equal to I. Does anybody see anything I can do to clean this thing up a little bit?
The A thirds.
Yeah, so the identity times A cubed is the same as A cubed times the identity. Remember, when you're multiplying by the identity, it's like doing nothing. So you don't really have to worry about that. Okay, anybody else want to help me with anything else? Jerry?
You can also remove IN that's multiplied by A6 and A9 because they're basically equal to 1.
Exactly, so I can kind of not think about the identity matrices that are there. Excellent. Other suggestions? What else can I simplify with? Alex?
I mean, now that you know the A's cancel out all the A's except A12.
Exactly, I have A to the sixth canceling with minus A to the sixth. I have A to the ninth canceling with minus A to the ninth. And on this identity squared, that's like 1 times 1, which is just 1. So I'll just write that as identity. So as we just pointed out, the only thing that survives there is the minus A to the 12th. But what do we know about that? Thomas?
0 there.
This one is just 0, right? Exactly. If you subtract 0, well, that's like doing nothing. So look what happens. You actually get your identity matrix at the bottom, which is exactly what we were hoping for. Okay, so there's your solution. There's your solution again. Yeah, Audrey?
You explain just the, like, why we want to multiply those things to prove what we're trying to prove.
The definition of two matrices being inverses of each other is that when I multiply them together, I get the identity matrix. So anytime you're claiming that the inverse of one matrix is another, you're going to multiply them together and hopefully get I. So we've done it already 3 times here, right? These 2 warm-ups, we took, you know, what the inverse of AB was, we multiplied it by that. We multiplied AB by its proposed inverse, we got I. Same thing here, same thing here. And you'll see a bunch more of them in the midterm resources. So that's the definition. That's what it means. If I claim the inverse of one thing is another, the way you convince me is Yeah, you multiply them together and make sure that you get I.
Is that what the statement under prove means, like the inverse of? Like,
This is telling me what I'm being asked to do. I'm being asked to show that the inverse of this matrix here, let me circle it, this matrix here, the inverse of that is this matrix here. So I have to take the two things that I circled and multiply them together. Notice I don't have a -1 exponent here. That's because it's not the inverse of this matrix that I need to check. I'm taking the matrix itself and multiplying it with its proposed inverse.
thank you.
Sure. Okay, let's keep going. We're on a roll with this. Let's look at 37. I think that might be a good one to do. It says on 37, suppose that the inverse, I'm gonna kind of abbreviate the words here and just write the equation. The inverse of a to the 5th is equal to b cubed. The question is, what is the inverse of a to the 15th? So the inverse of a to the 5th is equal to b cubed. And we want to figure out, well, what would be the inverse of a to the 15th? And you might even have a guess as to what you think the answer is. But I want to justify it. I want to write down the math that would go along with it. So this first assumption here, right, tells me that we know that if I take a to the 5th and I multiply it by b cubed, what am I supposed to get? The identity, right? Exactly. So we know that. We know that because they told us that the inverse of a to the 5th was b cubed. But what this means, guys, is that every time I see 5 a's followed by 3 b's, right, they cancel out. You can cancel them kind of as a package. So you take the 5 a's and 3 b's, you can wipe it out. So does anybody have a guess as to what they think? This problem is different than the last one. They told you what the inverse of the matrix was supposed to be, and all you had to do was verify it. Here they haven't told you yet what the inverse of a to the 15th is. Does anybody maybe have a theory or a guess as to what it maybe should be? Audrey.
B to the 9th.
B to the 9th. B to the 9th would be my answer as well. And that is going to turn out to be correct. Let's see if we can understand why that would be correct. It's like you have tripled the amount of A's. So to get the inverse, you would need to triple the amount of B's that you have. So you go from 3 B's to 9 B's. But let's check it. Let's check it. So let's just note that if I take A to the 15th times B to the 9th, what would I like this to be equal to, hopefully? The identity matrix, right? Because I'm trying to show that the inverse of A to the 15th is B to the 9th. So hopefully this equals I, right? But see, here's the deal. All right, bear with me. I'm actually going to write out 15 A's. There's 15 A's, and then I'm going to write out 9 B's. Okay, write all that out. But remember, what we said initially was anytime I see 5 A's followed by 3 B's, I can cancel them. Does anybody see anywhere in there where I have 5 A's followed by 3 B's? I think so, right? Like you can't start at the left, right? You can't cancel these 5 A's with these 3 B's over here. But if you look in the center, right, I see 1, 2, 3, 4, 5 A's and 3 B's. All of that is just the identity, right? 5 A's followed by 3 B's. So if I cancel all that, right? If I cancel all that, then what I'm left with should be, I only have 10 A's left. Go ahead and write them all out again. And I only have 6 B's left. I'm just doing this step by step. You could probably make it a little shorter, but I just want to kind of show all my work here carefully. What do you suppose I'm going to do with that? Same thing, right? I'm going to take 5 A's and 3 B's, and I'm going to cancel those again to the identity matrix. All right, and that leaves me with only 5 A's now and only 3 more B's. And sure enough, we already know that that is the identity matrix, so we'll check that one off also. We'll check that one off also. Okay, so there you go. The inverse of A to the 15th is B to the 9th, and that's your little proof. That's your solution. Okay, fantastic. So far so good. Number 39 is also on the board, as long as we're on this section. 39 is also on the board over there. However, I'm going to ask you to see your notes from last Thursday, which would have been the 12th, I believe. I actually did that problem in your notes. You'll see it somewhere. Specifically where I asked you, can a matrix have 2 inverses? We eventually said no. If there's an inverse, it will be unique. And in the course of explaining that, I basically did number 39. So I'm going to let you look at that in your notes again, just to make sure you've got it down there. Okay, so I'll leave that one for you guys. While I'm talking about the homework, I might as well, let's look at number 15 from this same section. By the way, this is all of the theoretical ones. I just did them all at the beginning right now, the ones that this is really at the end of homework number 6. All of the rest of the problems on that sideboard over there are much more computational, like number 15, where they give you the matrix A, and I'm just going to write it here for everybody, 2, 1, 3, 1, negative 1, 2, and 3, 3, 4. We take that matrix. Then they ask you to find the inverse of A, if possible, by using the Gauss-Jordan method. So the Gauss-Jordan method, we need to kind of remember how that worked again. For the Gauss-Jordan method, it's what we explained last week, right? We put our matrix into a block here on the left side. So I go ahead, I write it down. And I augment that with an identity matrix. So in this case, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you start off with, you know, A on the left side and the identity matrix on the right side. And if you remember, what you're supposed to try to do is turn the left side into the identity matrix, because if you can do that, then at that moment, when you achieve the identity matrix on the left side, the inverse of A shows up on the right side. Everybody remember that? Right, so you start, just to recall, just a quick review from last week, we're going to try and do some EROs, and we try to get the identity matrix on the left side, because if that happens, then the inverse of the original matrix will be on the right side in that same moment. So on this one, can somebody suggest a good ERO to kind of get started with here? Yeah, I would get this 1 that's in the left column, right? I get it up to the top left corner. So I would do P12. So I will do that with you. I'm going to do this fairly quickly, guys. I'm just going to permute the first 2 rows. All right. I get something like that. And the reason for doing that is that it creates a pivot here. Guys, I've been seeing some people in my office hours not circling their pivots. And although it's not really required, it's so helpful to do that, right? It helps you keep track of where you are in the ERO process. So I'm going to circle my pivot there, which is a 1. And now the top priority is to get zeros below that pivot. And this is where I'm going to use the A operation. So what A operation would I want to use for the first and second row? A1, 2 of -2. And I'm going to do the first and third row at the same time. What operation would that be? A1, 3 of -3. Let's do them both at once. Okay, so we leave the first row the same. Whoops. Go too fast. Actually, guys, is the worst thing you can do is rush through this. I'm just going a little fast just because I know this is not as interesting, and we probably don't need to dwell on it too much. But anyway, so I take -2 times the first row and I add it to the second row. And then I'm gonna take -3 times the first row and add it to the third row. So we'll get something like this. That should be about right. Okay. That look okay so far? But guys, what you're gonna notice now is if you kind of look right here, you can see that if you take the A operation, the adding operation with the second and third row, so in particular, if I do A2, 3, and I use a multiple of -2, what you can see is going to happen, I won't write out the whole thing again, but what will happen on the bottom row is, and I don't even care what's over here or anything else, I will get a row of zeros there, right? I will get a row of zeros there, and that is a red flag, actually, that you are not going to be able to get the left-hand side to become the identity matrix. When you get to this kind of a spot here with a row of zeros now, it's not looking too good, right? It means that this matrix is actually not invertible. So this one is actually not possible. And that may be why it ended up on my sideboard over here, is because it's a little bit surprising that we have a matrix that somehow, oh, it doesn't have an inverse. And that's not obvious when you just look at it. I want to make that very clear. You actually have to take the time to work with the matrix a little bit in order to figure that out. Okay. Does that make sense? Is there any questions on that? This is number 15. It does not have an inverse. And you can stop when you see this, guys. Remember our little theorem. I'm going to transition now to kind of some notes again. We'll maybe come back to the homework a little later on today. I just want to remind you of this theorem where it said, the following are equivalent. We talked about this last Thursday. I just want to get it back up here one more time because it's really important. We had, the first statement was part A, the matrix capital A is invertible. And then there was a part B that said, if you had a linear system like AX equals B, it has a unique solution. Right? In fact, we even know what the solution is. Remember, it was just X equals A inverse times B. So if the matrix A is invertible, then we know how to solve a linear system for the unknown. It's just the inverse of A times B. Okay, and then I'm just going to go ... But somewhere along the line, there was a statement that said that the rank of an invertible matrix should be n, full rank. And guys, if you take a look here at this matrix, n is 3. It's 3 by 3 matrix, yeah? But what's the rank going to be? How many pivots? If I just look at the A side of the matrix, how many pivots? I can only have 2 pivots there now, right? Because that third row is all zeros. So this is a matrix. In this example, this matrix does not have rank n. And so therefore it is not invertible, right? This whole list that we're making is a package deal. Everything in that list has to be true about your matrix or has to be not true about your matrix. You can't have some things true and some things false here, right? It's either all true or all false for any given matrix A. I should say here, let A be an n by n. It's always got to be a square matrix. Okay. And so we have this whole list, right? I think we got all the way as far as F. And we said, okay, A could be row reduced to the identity, which is kind of the fundamental idea behind the Gauss-Jordan method, is that if your matrix is invertible, you should be able to take it and reduce it to the identity. And again, that's not happening here. This matrix is not reducible to the identity matrix. You can do EROs for the next 10 hours. You're never going to get the identity matrix over here, you see. So that's kind of good to put all of that back together again one more time. But I had mentioned on Thursday last week that there's nothing in this list that's like really that easy to work with. Right? So, I give you this matrix on number 15 and I say, is it invertible or not? And we sort of have to throw up our hands and say, I don't know, I guess I'll have to do a bunch of EROs and see what happens. And we mentioned this on Thursday that wouldn't it be nice if there was a better test for invertibility, a better way of deciding is this matrix invertible or not? And it turns out that there is, and I'd like to start talking about that a little bit right here. So this is the topic of chapter 3. It is something called determinants. It is something called determinants. So we're going to discuss this idea right here. Determinants. This is going to give us a different way of thinking about invertibility. And I'm going to be adding a statement right here. If you want to, you can kind of pencil this in on your notes. We're going to talk about something called the determinant, det of A. And this is going to be just a number. And as long as that number is not 0, we're going to say that the matrix is invertible. This is going to be the condition. This is what we're going to be looking for. We're going to take our matrix. We're going to calculate some number with that matrix. As long as that number is not 0, the matrix is invertible. So that's the idea, right? The idea is given your matrix A, which is n by n, what we're going to do is we associate a number, and this number is written det of A, or you will sometimes see it written this way, guys, and even in my book it's written this way a little bit. You put the A kind of inside of these bars that look like absolute value bars. This is not absolute value bars. It's a different notation. I'm not a huge fan of that notation, but unfortunately it's kind of standard. Everybody in linear algebra land sort of is built to understand and be comfortable with this. So anyhow, we have to kind of live with that notation, but you're going to see me write it as det of A all the time. And so that is what we're going to do. And the importance of determinants. Oh gosh. This reminds me of a kind of a funny story. So there is a professor at Cal State, at the University of California, San Francisco. He's a professor at San Francisco, and he wrote a book on linear algebra, just linear algebra. And he's a very well-known mathematician. His name is Stephen Axler, and he wrote a book, and he called the book Linear Algebra Done Right. That was the name of his book, Linear Algebra Done Right. And I have a copy of the book, and I started looking through it, and then I looked at the chapters. And he has a chapter whose title is Down with Determinants. So I started looking through his book a little more detail. I realized, oh, this guy doesn't like determinants. And he basically wrote a book where he did all of linear algebra as best as possible without ever discussing determinants. He tried to avoid it at all costs. Like he wouldn't give you this line. He would just focus on everything else, right? Down with determinants. That was his motto. He just didn't like them. So then my PhD advisor is over across the bay at Berkeley, which is on the east side of the San Francisco Bay. And so he's also an algebraist, and he wrote a book in non-commutative ring theory. And I was looking through his book when I was a grad student there, and he has a chapter in his book called Up with Determinants. And I think these guys like know each other pretty well. They both live in the Bay Area. So the one guy's responding to the first guy's chapter called Down with Determinants. And so, of course, since my advisor is my friend and helped me out so much in my life, I have to agree with my advisor that I think determinants are awesome. And they are very important, and I can give you lots of good reasons why we should care about this. So anyway, it's an interesting little joke that my math friends played with each other. But let me give you a few quick reasons why we should care about determinants, okay? Hopefully you'll agree with me that we should promote determinants more often. So the first one is it is going to be, as I mentioned already, a test for invertibility. A test for invertibility. So I've already kind of given you how that's going to work. We're going to calculate this number, whatever it is, and as long as it's not zero, my matrix is invertible. So we'll be able to do that with this one, for example. We'll be able to take this matrix. There's a number that we can associate with it. I'll explain how we get that number in just a minute. But once we have that number, we'll be able to decide whether the matrix is invertible. And if it's not invertible, then we can save ourselves all this extra hassle, right? We know it's not going to work. And so just don't bother doing all these ERO. So I like that. A second reason why determinants are going to be helpful to us, so I'll talk more about this today, which is September 17th. Probably we wait until Thursday. I'm going to give you something called the adjoint method for A inverse. So I'll refer you in your notes to Thursday because I won't have time to get to all of this today. But there's something called the adjoint method. This is an alternative way of actually finding the inverse of A that does not involve the Gauss-Jordan method. If you don't like EROs very well, I have a bailout option, which is to do something that's more determinant based. Okay, so we'll talk about that. The third one is something called Cramer's rule for solving A times X equals B. So if you actually have a linear system and you have your coefficient matrix here, capital A, then again on Thursday, I'm going to explain a little bit about how you can solve a linear system using determinants. Okay, so instead of having to do Gaussian elimination or anything like that, we can avoid EROs. All of this is about avoiding EROs, right? And then there's a fourth application, which is kind of a geometric interpretation. So a geometric interpretation, there's some geometry that we can discuss that's related to this number that we're going to be talking about. And this one is going to most likely come a little bit later. It becomes much more useful to us later on when we get to chapter 4. So I'll just give you that as a preview, as a point of preview here. So if I do my job right, I should get through all 4 of these bullet points soon, and you'll actually hopefully agree that we should be thinking up with determinants here, because they are actually very, very helpful. Okay, so let me start off explaining a little bit how we find determinants. Right, so first of all, so for number 1, right, let me just go, I'm gonna just explain number 1 right now. A, which is n by n, is invertible. I've already said this, I just want to get it very official for the notes. If and only if the determinant of A, whatever that means, is not 0. So that is your test for invertibility right there. A matrix is invertible exactly if this number that we calculate is not 0. Okay, so now I need to calculate the determinant. So what is the determinant of a matrix? So this is mostly what we're going to talk about today, is how do we actually find this number? Well, I'm actually going to explain it for a small matrix directly, and then we'll get sort of the larger matrices after that. If I just have a matrix that's just a 1-by-1 matrix, so again, it has to be a square size, guys. If the matrix doesn't have an n-by-n size, this whole chapter is kind of not going to apply at all. Okay, but if it's just a 1-by-1, you could imagine that the determinant of a 1-by-1 matrix is just going to be that number. If we build it up to a 2 by 2, so we have A, B, and then C and D. The way we find this determinant is, well, this is gonna look familiar from last week. I gave you the formula for the inverse of a 2 by 2 matrix, and it involved AD minus BC. Okay, and you might even remember that the formula for the inverse of a 2 by 2 matrix, which I gave you last time, involves dividing by AB minus BC. So I really do need it to be not 0 for that to even make sense. Okay, so these are just formulas for how you calculate this number that is associated with the matrix. Let's do the 3 by 3 case. I think I have just enough room here to write it down. So suppose I have A, B, C, D, E, F, and then I have G, H, I. Suppose I have a 3 by 3 case. So I'm gonna squeeze this in over here. If you need to stand up in the back, feel free to do that. Because I'm gonna have a few terms. Actually, before you write that equal sign, when you're taking notes on this, could you leave just a little bit of space here? Because I'm gonna actually write something into that space in a moment. But give yourself just a little bit of room. I'm sorry about that. I should have warned you for that. But the formula here is AEI plus BFG plus CDH. And then we go minus CEG and minus AFH. And then minus BDI. Okay, that's the formula for a 3 by 3 determinant. That is the formula. Before you start panicking that you're not going to remember this correctly, because there's like 9 different letters and kind of a messed up alphabet soup of terms here, there is an easy way to remember it. And the easy way to get this formula right every time is the reason I asked you to leave a little space here. Because what you can do to remember this formula, which I would recommend because there's going to be a lot of 3 by 3 matrices, is you can recopy the first 2 columns of this matrix just off to the right of the matrix itself. So you recopy just the first 2 columns. And then here's how you're going to get the formula right every time. You're going to start drawing these diagonal lines across the matrix. So you see this first diagonal here, the main diagonal, AEI. And then if I just shift to the right, the next diagonal becomes BFG. And if I shift to the right again, the next diagonal becomes CDH. So you take all 3 of those diagonals and just sort of multiply the entries and add them together. And then you notice that there's 3 more terms that have minus signs in front of them. That's obtained by doing diagonals the opposite way. CEG. And then the next one is AFH. And then if I shift to the right again, I get BDI. So 3 more diagonals going the other way. This is how I tend to remember this formula. And I like to refer to this as the arrow method. Okay, so we're going to talk about using an arrow method. Actually, let's be very clear. This is an arrow method for a 3 by 3 matrix. There's always somebody every semester who tries to invent a 4 by 4 arrow method, of which there is not one. Okay, there is no good method for a 4 by 4, so don't use this kind of thing on a larger matrix. It's only for 3 by 3s. Okay, so with that in mind, let's just try this. Let's just try this number 15 here that we already still have on the board. So just as a quick example, if I wanted to do the determinant of this matrix, so 2, 1, 3, 1, -1, 2, and 3, 3, 4. So if that's my matrix, then let's try this arrow method on it, right? So I'm going to recopy the first 2 columns. So 2, 1, 3, we'll copy the first column there. And then the second column is 1, -1, 3. We copy those first two columns, and now I'm gonna get busy doing my arrows. Okay? So go ahead and put equal sign here. And I'm gonna draw my first arrow, goes down the main diagonal. That's 2, -1, and 4, which becomes -8. Okay, and then the next arrow to the right of that is 1 times 2 times 3, so that's adding 6. And then the next arrow to the right of that is 3 times 1 times 3, which is 9. Like that. Okay? And then I keep going, I have to subtract the arrows that go the opposite way. So here's the red arrow, 3 times -1 times 3, that's minus -9. Okay, and then the next arrow to the right of that is 3 times 2 times 2, which is 12. So I have minus 12. And then the next arrow to the right of that is 4 times 1 times 1, which is 4. So we go -4. And we just have to add those numbers up now. So let's see, -8 plus 6 is -2. We add 9, that becomes 7. Add 9 again, I get 16. Now subtract 12 and subtract 4, you get 0. You get 0, which is absolutely what we already thought we would get, right? Because we said earlier, this one was not invertible. And my theorem here says, yeah, if you get determinant of 0, then the matrix is not invertible. So we're kind of confirming that. Wouldn't that have been nice? Before you did the homework assignment, if I would have showed you this, you said, oh, I just have to calculate this arrow method, I'll get 0. That'll save me, 5 minutes of struggling, maybe 10 minutes of struggling with EROs, right? To get to the same point. So now we have this really cool thing that we can do, which is the determinant of the matrix. Does everybody understand that? Make sense how that works? The only thing with the arrow method is just don't try to use it on a larger matrix. Okay, it's really for 3 by 3 size only. So the question then becomes, what about the determinant of A when n is at least 4? What would be the determinant of A in that case? And you guys know how I roll by now, 4 weeks into the semester. I always like to kind of tease you a little bit, make you have to wait for the answer. In this case, I'm going to make you wait all of 10 minutes. We're going to take a little break. Unfortunately, I don't have a direct formula for you. Essentially, what you have to do is, again, a process for getting the determinant of a larger matrix. So I'll explain that process after I give you guys a little chance to decompress. Let's take 10 minutes. At about 11:15 or so, we'll pick this back up again. Okay, so go ahead and take 10 minutes. Yeah, sir. Oh, I'm gonna explain. Yes, that is something, you already know something I haven't taught in class yet, but I'm gonna explain.
So you're giving me an
Yes. Yeah, that's great.
I spent like 20 minutes trying to figure it out. And then I was like, I'm not mad. I'm so mad. It's kind of funny. I didn't realize. I see you. Really?
Mm-hmm. That was just like your spot, but then I was just starting and I guess
I was literally gonna text you like I'm gonna be there right now. Make sure nobody takes mine.
okay, I feel like somebody's sitting here. No one's here, it's okay, and it's me.
Yeah. Imagine.
Then, oh, I'm not gonna be in silence later. Why? I'm sorry. She says anything about the exam I'm gonna make. You know, I have a solids exam and a fluids exam on the same day, and I have the classes back to back.
Is it next week?
No, it's next week. On Wednesday, and I have solids and fluids back to back. Not
Next
solids,
Wednesday?
dynamics.
This Wednesday?
Dynamics,
Oh,
next Wednesday.
we have math.
Yeah, on Thursday, the day after.
You've 3.
I'm genuinely back to back, like my classes are back to back.
Oh yeah, mine too.
Oh,
I
you
go
have-
from dynamics to fluid mechanics. And then I have math the next day.
Oh,
I know. I thought I was. I mean, what are you gonna do?
It is what it is.
I'm not gonna worry about dynamics as much. How I feel, I'm like, whatever.
Cause I was using my guard down, cause I'm like, okay, my easiest class.
No, I'm still gonna study.
Yeah, I'm gonna study, but I'm not gonna study.
Math is more important.
Yeah.
I feel like they're the same amount of unit, or no, they're, I guess they're not. But like technically they are like the same level of importance. They always make math first. I always put it first. I don't know why.
Genuinely. That's why they give you that.
Should be like 2.
Oh, I sat next to a girl in my fluid mechanics class that had our professor for dynamics last semester. Well, she said that the way that she does the quizzes and exams is similar, like, you know how like she'll just write on the board during the quiz.
Yeah.
She said that like her exams are that hard. She might, and she's helpful like
Really?
and like I think the equation sheets are already up, so we already know what we have to have memorized and what we have there. How did you guys we put the same thing. H/2. I think. Well, they were all H/2.
Equal.
Oh, okay. Yeah.
So all 3 get it wrong.
Well, I mean, then we all get 70%. We put
I
our
was
names on the
thinking
paper, we
that.
pass.
I was like, if I mess this up right now.
Has she put the other grade in? She has to have, right? Because she gave us our quizzes back.
Yeah, but she didn't grade the homeworks. I
Oh,
hate when they don't do that, because then I'm like, what if I'm doing something wrong this whole time and like,
well, she said she does it for completion.
but formatting wise?
Oh, formatting wise.
So you have to like put your name or something.
on every page. Yeah.
Yeah.
You did? Yeah, you're supposed to.
It says it in the description. Rip.
Well, my first homework was only 1 page. I don't remember how many pages my second one.
Homework submissions must have everything.
The name at the top.
It's like in the numerical.
Oh, I forgot, guys.
Okay.
Yeah.
You're good, you're good.
And I don't have an excuse for homework too, actually, but.
One of my classes, I had to write my name, my CWID, the class,
Why so
something else on
Oh.
every single page. And I was stressing. I was like, what if I forget what page? Yeah.
It's really like, yeah. Each one is the enemy page and it's the legend number. Legend page number. What is it like?
I have so much graphic engineering.
Like 3, like 2.5.
Yeah.
Things of it.
This is the one with the graphic engineering graph paper. Oh, I'm on this one. I did 25.
That's a lot to write down. I swear, most of the time I spend doing the homework is coffee.
Professor, in your office, are you gonna get the other whiteboards back, or is it just?
I think so, yeah, I am frustrated because they said at the spring, they're like, oh, it's gonna be so great in there. And then I find out like by the end of the spring, they took everything out, but they didn't put the new stuff in yet. So that is supposed to be happening, but I wouldn't hold my breath when it will happen. So hopefully before the semester's over. So you're not the first person who's kind of noticed that. But you can always come into my office and use my board,
Yes, you're right.
which is actually a nicer board.
And they're raising candy during study sessions last.
Exactly. Feel free. There's already people figuring out that that's where they can get some good work done. Sore.
Did you climb the mountain?
I tried to on Sunday. It didn't quite go as planned, so I got partway up it and then came back. But I'll try it another time. Kind of got myself lost a little bit, but it's okay. It happens. Yeah, it was good to, get out.
here to not give me that. Yeah. I can move it.
Yeah.
I'm just gonna start a new page. I think. I think this. Yeah. But I meant the like most of the space, it's just coffee. There's a Panda Express. Is there anything? There's a Togo's. There's a Biology.
I didn't go grocery shopping this week and I kind of don't feel like getting my parts and maybe.
There's also a Habit and a Wingstop and a McLean.
Like, then I thought,
Yeah.
it's like not even.
I miss when there was an 85 degrees.
There's one by way of Herman.
Is it still
But,
open? I thought
underneath.
it closed.
No, it's not.
I thought
When?
recently.
Oh, recently.
Yes. They have it.
Oh,
Oh, bagel. In the same spot. I eat bagels for dinner all the time.
I mean, true.
But if you get like stuff
get
on the bagel,
crash.
then it's a sandwich.
That's true.
Just get stuff on it and it'll be good. Stuff counts.
Those hungry.
All right, guys, I think maybe I'll go ahead and pick things back up here again. The other two problems that folks wrote up on the board here class are two that I often get in my office hours questions about, so I thought it might be good to discuss them a little bit together. I am gonna warn you, though, that I'm gonna be a little sketchy in terms of doing the EROs. I'm gonna kind of skip that part and get to the interpretation of the conclusions here. So just to remind you guys, kind of going back a little bit, that when we have a linear system of equations, whatever it is, there will always be either, well, I've written them here, either 0 solutions, 1 solution, or infinitely many solutions. Like those are the 3 possible scenarios. And I hope you remember from last week that which of these scenarios comes up depends on how the pivots end up in the row echelon form. So you're going to take your linear system, and you see I've done it already. I take my linear system, you put it into an augmented matrix. So I did that for both of these two problems on the board behind me here. And then the idea behind this is to bring those matrices into row echelon form. And then depending on where the pivots are, that will dictate whether your system has no solutions, 1 solution, or infinitely many solutions, right? That's kind of the idea. Right, so you probably remember, like, if you get a pivot into the far right column, that means no solutions, right? If there are unpivoted columns to the left of the bar, that means there's free variables. Free variables would coincide with infinitely many solutions, right? Otherwise, if there's no free variables, then you'd have 1 solution. So these are kind of the 3 possibilities. It all just depends on the pivots. Now, if we look at number 25, look what all of the equations are equal to on the right-hand side. This is, whenever this happens, by the way, I think this word does come up in the homework, so I should mention it. It is called a homogeneous linear system when you have all of the equations equal to 0. That word homogeneous just gets used way too much in Math 250B. We use it so many times, but it comes up here as well. So this is a homogeneous linear system. It's got all zeros on the right-hand side, which means when you augment the matrix here, the far right column is all zeros. So I have a question for you. Will that far right column ever have a pivot in it?
No.
You start doing EROs, right? Permute 2 rows or multiply a row through by a constant or anything like that. You're not going to change that column of zeros, right? So you will never get a pivot in the far right column. It doesn't even matter what K is. So this whole problem was to determine values of K that would give you all 3 of these outcomes. But what I'm trying to say right now, guys, on problem 25, you will never be in a situation when there was no solutions. In fact, you can even tell me what one of the solutions is. just by looking at it, you can see that if I put in 0 for all of my x's, so the solution 0, 0, 0, 0, right, works. It solves all the equations. And so, of course, yeah, you have at least one solution to this system over here. For sure. So we're never going to see no solutions on number 25. Now, the real guts of this problem, though, is this k value, right, which shows up in the matrix right here in the setup of the augmented matrix, is going to change as I do my EROs. And this is where I said I'm going to be a little sketchy about the EROs. I'm going to let you guys kind of check that this is sort of the form. Remember that below all these pivots, these are all zeros, of course, right? And there's some numbers over here. I don't even care what they are, right? But the shape of the pivots are right down the diagonal. I have a 1, a 1, a 1, and then I'm actually being a little bit incorrect to put a pivot around this k plus 1. This should become k plus 1. If you don't end up with a k plus 1 down here, guys, it means there's some problem with the EROs. And you could check with me at the office hours about that. I'm just going to write it down right now. This should be a k plus 1. That could be 0, right? If k was equal to what value would I have actually this not being a pivot? -1, right? If k was -1, then this would actually be a 0 right here. And if that was a 0, then is there a pivot in this column? Not at all. And if there's no pivot, it means that in this case, x4 would have been what kind of variable? A free variable. And if there's a free variable, that's infinitely many solutions. So if k is equal to -1, right, we're going to get infinitely many solutions there, because there's actually no pivot in this far right column. Now, what some people have been doing on the homework is they've been saying, well, if it's a pivot, it's going to be equal to 1. So I've seen people doing this. They say, oh, k plus 1, if that equals 1, then this is a pivot. Which, that is true. So in other words, when k is equal to 0, but actually, if k plus 1 was any number other than 0, you essentially would have a pivot there. Even if it's not a 1 yet, you could make it into a 1 by just dividing by whatever that number was. So what I'm trying to say is that instead of setting k plus 1 equal to 1, don't do that. What you should do is take k plus 1 and instead set it not equal to 0. That's a better way to express the condition on k. As long as k plus 1 is not 0, this will be a pivot. And now you have 4 pivots. All 4 of your unknowns are now pivoted, meaning there's no free variables. But we know that you have to have a solution. So that would be this case. K does not equal -1. So as long as k does not equal -1, you would have exactly one solution, a unique solution. So that's kind of the breakdown. You can never have no solutions there, but depending on whether k is equal to 1, is equal to -1 or not, you'll get the other 2 cases. Okay. So guys, 26 is similar. I won't, again, do all the details here. This one's a little harder in my opinion, just because there's 2 parameters here, the A and the B, that you have to kind of consider together. And as before, we just start off by putting the system into an augmented matrix. I've just recopied it here for you. And then I'm omitting again. This is a good office hour chat if you're having any trouble with these EROs, but I'm basically just going to hit this matrix with EROs. And I'm not going to flinch about the fact that there's A's and B's floating around. Those just go along in the matrix just like any other number would. And you should end up, hopefully you get something that's looking like this here. If that's not what you had, I can take a look at your work and try to straighten you out. It does take a few steps to kind of get this form. But the point here is I'm going to circle my pivots again. And I have this bottom row is really where all the action is, right? This 2a minus 3. So guys, 2a minus 3 if that is not equal to 0, so same thing I did here, k plus 1 not equal to 0, 2a minus 3. If this is not equal to 0, then my friends, this would be a pivot. Or it could be turned into a pivot. And remember, if my pivots look like this, right down the diagonal, how many solutions does my system have? Is it 0, is it 1, or is it infinitely many? If the pivots are here, here, and here. One solution, that's right. So this would be the one solution case. And this, of course, just means that a does not equal 3/2, if you just sort of solve that around. So in the case when a does not equal 3/2, we're going to get one solution. Now, people sometimes will ask me, well, what about b? Because there is a b in this system here. But as it turns out, in this case, b can be anything. It doesn't even matter what b is, as long as a does not equal 3/2, we will end up with one unique solution. What if a does equal 3/2? If a does equal 3/2, then this number right here is actually a 0. And now your bottom row is 0, 0, 0, and then the all-important expression on the right-hand side, negative 2b plus 20. That's what this says here, negative 2b plus 20. And depending on whether that is 0 or not, we might have a pivot over here. Right? So in fact, if negative 2b plus 20, if that's not 0, which in other words means b does not equal 10, if b does not equal 10, so in other words, if a equals 0 and b does not equal 10, we're going to get a pivot in the far right column. And that's no solution. So this would be a equals 3/2 and b does not equal 10. In that case, we would get no solution. And then finally, the last option is, well, what if a is equal to 3/2 and b does equal 10? So if both of those are true, well, then your bottom row of your matrix here is just 0, 0, 0, 0. And in that case, you actually have a consistent system, and you even have a free variable, because this would have no pivot. That third column would be unpivoted. So you have a free variable there. So I'm just, I'm skipping the EROs here. I'm trying to discuss how you interpret this pseudo row echelon form here. It's not, I'm not saying it's totally row echelon form, because these numbers may not be ones that have the A and the B in them, but you kind of get the idea here. I wanted to show you how this analysis kind of works. Questions on this? Do people follow what I'm doing here? I have been known to put something like this type of problem on my exam. My SI leader, I'll remind you, Janda Huang, he was here the very first day we came back in person. He is welcoming everybody to his sessions. I think they've been pretty popular. A lot of people going on Tuesdays and Thursdays at 4 o'clock. He told me he's going to do at least one more of these in full detail in his session today. So if you happen to be interested in seeing that, feel free to do that. Or you can watch my review session video for the midterm. I have a problem in that set of resources that also kind of gives you a little more practice with this. But anyway, I thought maybe if I just give you at least the outline here, you get the idea. Okay. All right, great. So I think I've covered quite a bit of the homework for you. I felt bad. It's 2 assignments due in one day. What's he doing? So anyway, now that we've done some of the homework, I feel a little less guilty about that. I should tell you that there is an assignment due on Thursday as well. The thing about the Thursday homework is if you understand this right here, just this, you can do that whole assignment in 20 minutes, maybe. I'm going to guess 20 minutes. It's very fast. It's just section 3.1, and it's only matrices that are very small. So this works great for the homework for Thursday. Compared to what you're doing for today, that'll be a breeze. I don't think it'll be too hard. I do want to start talking, though, about what to do when the matrix is larger than 3 by 3. So if we had a 4 by 4 or a 5 by 5, how we could find this determinant. We don't have an arrow method for it, right? We don't have a nice formula for it, at least not so far. So I'd like to discuss here the last part of our time today. I'd like to try to get into what do we do when we want to take determinants of larger matrices. So I need to actually write down a couple of definitions here, okay? So let's see if we can make sense of this. I'll put a definition here. And I'm going to talk about something called a minor of a matrix. So I'll call this the I comma j minor. And I'll denote this as M sub ij of my n by n matrix A. So the ij minor, this is the word I'm going to explain right now. The ij minor of the matrix is the determinant. So it's also going to be a number. Remember, the determinant is a number, and it's going to be the determinant of the n minus 1 by n minus 1 submatrix. It's kind of a weird term, but I'll explain it in a second. I think you'll see what I mean. It's a submatrix obtained by deleting row I and column J. Okay, it's a bit of a mouthful. So we're going to delete a row and a column, from A. So it's going to be obtained by deleting row I and column J from the matrix A. So let's actually just do an example of that right away. And I'm going to go ahead and jump up to a 4 by 4 matrix here to talk about this one. So let me make a matrix for you here. Maybe 1, 2, 3, 4. And then on the second row, -1, 1, 5, -2. And then the third row, I'll use 0, 3, 0, -1. And then the fourth row is going to be 2 and -2 and 1 and -3. Be sure to copy that down correctly. This is a 4 by 4 matrix, and this matrix has 16 different minors, right? You have M11, which is the 1, minor. You have M12, M13, and so on, all the way. The last one would be M44. There's 16 different minors here, but at the risk of not boring us to death, I'm going to only ask you to find one of them right now. So let's find... This is the problem I want to do. Let's find M34. We're going to practice that one here. Get myself a little space over here to do that. So M34. Let's see if we understand how to do these minors here. Okay. Well, so what's it say? It says it's the determinant of the smaller submatrix obtained by deleting row 3 and column 4. So row 3, the third row, I get rid of it. The fourth column, I get rid of that. This is M34, row I is 3, and column J, the J is 4 here. Okay, so M34 would be the determinant of the matrix that we are left with now. So if I only look at the numbers that have not gotten crossed off, this should make a 3 by 3 submatrix. So I'm just copying again the numbers that are not in row 3 or column 4. So it should look like this one. Okay. That should be it. And well, what you've noticed probably is that we started with a 4 by 4 matrix, and now we're looking at a 3 by 3 submatrix. And once we're down to a 3 by 3 matrix, we can find the determinant by using the arrow method. So that's exactly what I want to do here, guys. I'm going to recopy the first 2 columns just to the right of my matrix, just like we explained before the break. I just recopy those first 2 columns, and now I go through and I do my arrows. So the first arrow is 1 times 1 times 1, which is 1. The next arrow is 2 times 5 times 2, which is 20. Okay, the next arrow, when I multiply it, 3 times -1 times -2, that adds up to 6. Okay. And then I do the arrows the other way, 2 times 1 times 3, but that one, now remember, we have to have a minus sign, that's -6. The next arrow is -2 times 5 times 1, that diagonal is -10, but I'm subtracting -10. Be careful with the double negatives, which do come up. And then the last arrow would be 1 times -1 times 2, so that's minus -2. Okay, if it helps you, you can, with these arrows, you can put pluses on the ones that are going down to the right, and then minus signs on the ones that are been drawn the opposite way. But this is what we just have to work out here, and I don't think this is gonna be too hard. The sixes cancel. 20 plus 10 plus 2 plus 1. I think that's just 33. I think that's just 33 if I do that right. So by the way, if we were interested in whether this matrix is invertible or not, since the determinant is not 0, the answer would be yes, it's invertible. And so now you could say, oh, okay, I'll go ahead and do my Gauss-Jordan method to find the inverse of this matrix. Or you can wait until Thursday when I'm going to explain the adjoint method for A inverse, which gives you another alternative way of doing it. But anyway, this is just for now calculating one of the 16 minors of this matrix. The good news here, guys, is you will almost never need to calculate all of them. We won't generally have to do that for what I'm describing right now. We'll be good enough to just do a few of them. Questions on this one so far? What the minors of the matrix are?
Right.
Yeah, Marco, what's up?
Just remind me, so if we didn't choose row 3 and like, let's say we chose row 2, then we'd have to multiply by the numbers in the row, or
Oh, you're thinking ahead. I'm not there yet.
not that?
I'm not there yet. I know what you're thinking about. You're thinking about cofactor expansion. But I'm coming to that shortly. Before I get to that, though, I just spilled out a word that I need to tell everybody about, which is what is a cofactor. So minors are related to something called cofactors. So let's do another definition here, guys. This will be the I comma j cofactor. This is another word in the theory of determinants that does come up. And this one, I'm going to write it as Cij of my matrix A, which is n by n still. So the ij cofactor of A is, here's the formula for it, guys. It's, I can actually just give you the formula here. And what it is you take the minor, Mij, and you maybe put a minus sign on it. So there is whatever the minor was that you calculated, you then multiply it in front by a power of -1. And of course, that power could be even or it could be odd. Remember, if you take -1 to an even exponent, it becomes +1. If you take -1 to an odd exponent, it actually becomes -1. So we could write this a little bit differently. We could say that this is Mij if I plus j is even, and it's negative of Mij if I plus j is odd. So this is just another way of thinking about it. There is sometimes a sign change between the minor and the cofactor. And when do you have to do a sign change? You do this sign change exactly if the I and the j, the entries, the subscripts of these minors and cofactors, if it adds up to an odd amount. To be perfectly honest with you, I tend not to remember it this way. The way I actually like to kind of think about this is with a little visual. And what I do is I say, well, look, if I start in the upper left corner, this would be the I value and the j value of 1. And 1 plus 1 is 2. And 2 is even. So there would be no sign change there. Okay, but then the next position over, if I and j was like 1 and 2, you add those up, you get 3. Okay, there's a minus sign associated with that position. right? And same thing with 2 and 1, that adds up to an odd amount, but 2 and 2 would be even again. And 3 and 1 would be even, and 3 and 2 would be odd. And I actually just remember that all you need to kind of do here, guys, I hope this is helpful. You're just alternating. These pluses and minuses just alternate throughout the matrix. And if you happen to be in an odd position, right, then, so the 3, 4 position would be 3rd row, 4th column would be right there. If you see a minus sign in that position, then you would need to change the sign. So in our example, from the above example, we can add this to the notes here as well. If we wanted to know the 3, 4 cofactor of the matrix that we were using over here in this example, do we need to make a sign change? Here's the minor. The minor was 33. So what's the 3, 4 cofactor going to be? Negative 33. And again, how do I know it's a negative? Well, 3 plus 4, that's 7, that's odd. I can look at my visual, I've got a minus sign in that position, so I'm gonna insert a sign change on whatever the minor was. So the minor was 33, so the cofactor is then negative 33. That's how this works. Okay. People okay with this? Any questions on the minors or the cofactors here? Are so good? So I think that I can now kind of explain how to do determinants when n is at least 4. I can now explain that, I think, in pretty good detail. So let's try and do that. We're going to use something, you already know it, and I know some of you already know this. This is something called the cofactor expansion theorem. We're going to use cofactors to calculate determinants. So let's state it here, guys. This is something you're going to definitely be using all semester. Cofactor expansion theorem. All right, let's see what this is about. Cofactor expansion theorem. Here is what it says. This is a big deal. This is really, really big. So let A be an n by n matrix. So we take a square matrix again. Guys, if the matrix is not a square size, we can't talk about any of this stuff. Determinants don't even, in that case, yes, down with determinants, right? For anything that's not square. Has to be a square size matrix. So here we go. A is a square size matrix. Then I am going to now be able to give you guys a formula for the determinant of that matrix. And I should mention that this formula actually will work even for a 2 by 2 or a 3 by 3 matrix. Of course, if the matrix is 2 by 2 or 3 by 3, I'd recommend the formulas that I wrote down earlier. That's probably the best way. But this formula is for any square matrix. If I want to find the determinant of it, I'm actually going to give you 2 formulas that are both good. The first formula is the following. I take AI1 times CI1 plus AI2 times CI2, and I go dot, 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 plus AIN times CIN. And just over here in the margin, it's kind of helpful to emphasize what we just did there. This is called expansion on row I. So here we're doing a cofactor expansion along row I. When you first look at this formula, it's a little intimidating because of all the subscripts, but let me just explain what's really going on. These AI1, AI2, and so on, that's literally just, if I look at my matrix, you could put this over in your notes in the margin, if it's helpful. If I think about the ith row of my matrix A, the entries in that row are AI1, AI2, all the way over dot, dot, dot to AIN. That's just the ith row of the original matrix that you have in your hands. Okay, so like if I'm doing cofactor expansion along row 3, this is row 3. This would be A31, A32, A33, and A34. And what am I doing over here? I'm multiplying those entries from that row by the corresponding cofactors in that row. You see that, right? AI1 gets multiplied by CI1. And AI2 gets multiplied by CI2, and I just add all of that up. This is the formula. Now, it turns out that you can actually also instead, if you don't want to use a row, you can use a column instead. So I could do A1J, C1J, plus A2J, C2J, and go dot, 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 up to ANJ, CNJ. This is also totally legit. And this would be considered expansion on column J. So, you also maybe somewhere here you have the jth column of your matrix A. So you'd have A 1J, A 2J, A 3J, and dot, 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 all the way down to ANJ. That would be the nth column of the matrix. Okay? Are people kind of following that? Sort of, kind of. What this theorem actually says is that you have a whole bunch of choices about how to get the determinant of A, because you can choose which row or which column you would like to expand on. Look at this matrix here. I can cofactor expand it along row 1, row 2, row 3, or row 4, or I could expand it on column 1, column 2, column 3, or column 4. That theorem is telling me, and I know it's a little deep and I'm not going to prove it right now, but this theorem is telling me I will get the same correct answer no matter which row or which column I choose. Right? That's the beautiful thing about that. I get to pick. I get to choose which row or which column do I want to expand my determinant along, you see? And would that ever make a difference? I mean, take a look. Let's go back to this matrix. I'm just going to recopy it here, guys. The matrix that we were just working with. Let's take A, which is the matrix. I'm just going to recopy it. 1, 2, 3, 4. And then the second row was -1, 1, 5, and -2. The third row was 0, 3, 0, -1. And the fourth row was 2, -2, 1, and -3. And let's say that I wanted to ask you to find, at this point, let's say I want to find that determinant. Let's say I want to find that determinant. So I'm going to have a question for you here. It's 4 by 4, so I don't have a simple formula. What I have is the cofactor expansion there, which tells me that to get the determinant of the matrix, I just need to cofactor expand along any row or column that I like. And does anybody see that there could maybe be a preference? Like we might prefer one of the rows or columns over another? Would our life be any easier if we chose one row over a different row? The row that has the zeros in them, guys. Do you see that, guys? Look at the formula. The formula has these AIJs in. If any one of those AIJs, like A31, A31 is 0. So if we take I equal to 3 in the first formula, A31 is 0. So do I even have to calculate the cofactor that it's multiplied with? No, because it's going to be multiplied by 0. Right? So I would suggest, and let's do this, I would suggest for our solution that we're going to expand row 3. Now, that does not mean that any other row would have been wrong. It just means that this will be the least amount of work. And since I only have 2 minutes left, I better make a good choice here. So let's do that. I'm going to do row 3. And row 3 says, well, it's A31 times C31 plus A32 times C32 plus A33 times C33 plus A34 times C34. This is just plugging in I equals 3 in the first equation. Right? That's exactly what I'm choosing to do right there. But the point is, A31, 32, 33, and 34 are just these four numbers. So this one is a 0 right here, and so is this one. So instead of calculating 4 cofactors, all of a sudden I only have to calculate 2 of them. Right? So what do I have? A32 is 3 times C32, and A34 was -1 times C34. The big thing here, guys, we have to be careful with the signs, the pluses and the minuses on this. Let's remember, I'm going to save a little bit of room here. C34, oh, we already worked that out. It was -33. I'm going to go ahead and feed that number in right here. This is from above. And with 1 minute that I have left, I am going to calculate C32. It gets multiplied by 3. Actually, let me give you another hint that I would recommend. I already know that this one has to have sign change, right? The 3 and the 2 adds up to an odd amount. So compared to the minor, there'll be a sign change. So what I actually am going to recommend that you do so that you don't forget about it is that you just go ahead and make that sign change right now. So before we've actually calculated the minor, let's take that 3 and get a minus in front of it. Okay? And now what I'm going to do, guys, is I'm going to come over here on some scratch since I'm almost out of time, and I'm going to calculate M32. So watch this. M32, remember how the minor worked? I know I just erased it, but we cross off row 3 and column 2, and we just do the determinant of that matrix that's still there. So M32, we've got a 1, 3, 4. We've got a -1, 5, -2, and a 2, 1, -3. And I'm going to wrap this up by hitting this with the arrow method. Okay, I'm going to do this kind of quickly since I'm out of time, but it's very easy. The first diagonal is -15. The next diagonal is -12. And the next diagonal is -4. And then I have to subtract the arrows going the other way. So subtract 40, subtract -2, and subtract 9. I did that kind of fast, but this is totally just numerical calculation. What does that come out to be? -27, -31, -71, -80. Add 2 to that back, so it becomes -78. I think I'm doing it kind of quickly, but I think it's -78. So that's the number that goes right here. So this becomes -3 times -78. And then we have plus 33 over here. Can somebody tell me what's 78 times 3?
230.
234?
Yeah.
So 234, and I'm going to add 33 to that. So that's 267, I think. 267. That's your determinant. If anybody wants to torture themselves, you can take this same matrix, try it again with any other row or column, and make sure that you still get 267. You have to get the same answer no matter which row or column you use. Just kidding about torturing yourself. Don't bother to do it. Just do the homework. All right, guys, and I'll see you in my office hours or else tomorrow, or else on Thursday. Have a great rest of your day today, guys. And stop by to introduce yourself. If you haven't done that yet, I'd love to see you.
That's been,
Just amazing.
Those are expensive.
Yeah, well, it was still in this case thing,
Yeah.
and so I didn't think to